Okay, to start this one off, they're asking us what is the potential energy at position A. So potential energy is equal to mass times gravity times height. So potential energy is equal to mass. It is 200 kilograms. So we have 200 times 9.8, and at position 8, the height is 140. So our potential is, wow, that's a big number, 274,400 joules. Okay, and that is part one. So assume there is no friction between A and C. What is the what is the potential at position C? Well, if we're at C, over here, then our potential energy is mass times gravity times height. Potential energy is equal to 200 times 9.8 times the height, which is 80. And we put that in the calculator. And we get 156,800 joules. Notice that this is less than this. That makes a lot of sense because we are closer to the ground. Some of our potential energy is no longer there. The third question says, what is the kinetic energy of the roller coaster at position C? Your first instinct is probably to go K is equal to mv squared divided by 2. But you get stuck really quick because you don't have the velocity. So what do you do then? You are going to always, if you have two positions that you're comparing, you're pretty much always going to want to use this equation. Ki plus pi plus work equals kf plus pf. So our kinetic energy initially, well, the roller coaster was at rest, plus our initial potential energy, 274,400, plus work. Would there be work? Well, there's no jetpack on the roller coaster. There's not talking about any engines, and they specifically said there's no friction and there's no air resistance. So in this situation, you could say work is 0 equals our K final is what we're looking for. That's our whole goal here. Plus our potential final, 156,800 joules. So we're going to do some math here and we're going to solve. And you should get a kinetic energy of 117,600 joules. For this last question, we have 117,600 joules of kinetic energy, and they're asking us, oh, it's the second last question, sorry. What is the velocity of the object at position C? Now, whenever they ask you for velocity, that's when you're going to want to bust out this K is equal to mv squared divided by 2 equation. It's the only one we have right now that has velocity in it. So if they ask you how fast something's going or the velocity, you're going to have to use this guy. So let's plug it in. 117,600 is equal to the mass was 200, velocity squared divided by 2. So I think the easiest way to do this guy would probably be to divide out 200 divided by 2 is 100 v squared. So you can divide by 100 on both sides. And that gets us 1176 equals v squared. So we're going to take the square root, 1176 equals v. I just recorded that without saying anything, sorry. So I had 1176 is equal to v squared. So I took the square root to get that, and I got 13.4 meters per second. It's really fast. And the reason it's so fast is because we assumed there was no friction between point A and point C. But we're not going to always be able to do that because the next question says, if there was between C and D, there was friction, how far or how long or how much friction is needed, so how much force is needed to stop the roller coaster. Let's try that one. Okay, this is going to be weird, but if we have, this is our initial kinetic energy, and at the end, we want the roller coaster to be stopped. So we're going to have 0 joules. So how much work is that going to take? Well, going along here, we have a really boring constant potential energy. So we can actually use this equation. Ki plus pi plus work equals AF plus PF. If we can solve for the work is equal to force times distance times the cosine of the angle. So if we can solve for the work, we should be able to find the force. What is the initial kinetic energy? That was that 1,17600 plus, what was the original potential? So the potential energy at that point was, if you look back, 1,56800. Okay, and we did that by doing mass times gravity times height for this position point C. Actually, it's not going to matter though because it's not going to change. Watch, I'll show you in a second. So here's work, that's what we're looking for. And final kinetic would be 0 because it's going to be stopped. Plus, here, look again, the potential is along a flat ground, so it hasn't changed. 1,56800. Okay, so it actually wouldn't have mattered. We could have said 0 here and 0 here because these guys are going to cancel out this and this. So when we subtract them, they disappear, so we basically end up with 1,17600 plus work equals 0. So how much work was done? Well, work is done 1,760. The work is getting rid of that kinetic energy. So that is the amount of work that's going to have to be done. They did not ask us for the work, they asked us for the force. So we can now do, okay, work is equal to force times distance times the cosine of the angle. The scariest part is this cosine of the angle, right? That's going to be negative. Okay, -1. How do I know that? Because we're talking about friction slowing something down. So if the cart is going forward in this direction, we know friction has got to be acting in the opposite direction. So it's going to be negative. The other way I can just know that this is going to be negative is because the cart isn't speeding up. Something has to be slowing it down. So there's going to be negative work here. And we already know there's negative work. It's right here. You can see it's negative. So we have work is equal to force times distance, so we have -1,17600 equals the force, okay, which is what we're looking for, times the distance. And it said it's going to take 120 meters to stop. So we're just going to divide that. So you would need a hefty 980 newtons of friction to slow that sucker down there. Okay, thanks. I hope you're having a good day.